In this video, we're going to look at how to perform some mathematical calculations involving calorimetry experiments. So calorimetry is a technique used to measure the amount of heat transferred to or from a chemical or physical process. Calorimetry takes advantage of the first law of thermodynamics, which tells us that energy can neither be created nor destroyed. It can only change from one form to another. So since energy can neither be created nor destroyed, the overall change of energy for a reaction must equal zero. So we could write this mathematically, saying that the heat absorbed or released by the system plus the heat absorbed or released by the surroundings must be equal to zero. So we can rearrange this slightly, as you can see here. Now here we have negative Q of system equals Q of the surroundings. So what we're saying in this statement is that the amount of heat lost by the system equals the amount of heat gained by the surroundings. Remember that the negative sign indicates that heat is being transferred out of the system, and the positive sign here means that heat is being transferred into the surroundings. So Q, or negative sign, doesn't mean less than zero, it's the direction of heat transfer. Now we could also express this equation as you can see here. Of course, in this way, we're saying that the amount of heat gained by the system, since we have a positive Q, must be equal to the amount of heat lost, hence the negative sign, by the surroundings. So in an equation like this, how do we mathematically calculate Q, either Q of the system or Q of the surroundings? Well, the heat released or absorbed by the system or surroundings can be expressed in terms of specific heat capacity. So we can calculate Q if we know the specific heat of the substance, the mass of the substance, and the change in temp. So these can generally be measured experimentally, and those will allow us to calculate the heat released or absorbed by the surroundings or system. Now we can also, if we needed to, we could also express Q and calculate Q in terms of heat capacity. So please be sure you go back and review specific heat, what that is, and heat capacity. But in terms of heat capacity, we can express Q of the system or Q of the surroundings if we know the heat capacity of the systems or surroundings and the change in temp. So if we wanted to express this equation here and therefore be able to calculate Q in terms of specific heat, again, we've just replaced Q of the system with the specific heat, mass, and change in temp of the system, and also of the surroundings. Now, in this particular equation, the negative sign is with the system, but we could very easily make the negative sign over here with the surroundings. I'm just showing you this as one example, but the negative sign is not always with the system. The negative sign could very easily be with the surroundings, which would give us a positive value for the system. Again, it's just whatever data or experiment we're given. Or if we wanted to express this equation in terms of heat capacity, it would look something like this. Again, the negative sign with the system, just as an example. The heat capacity of the system times change in temp is equal to heat capacity times change in temp of the surroundings. Okay? Or any combination of these two. So let's take a look at an actual problem involving some calorimetry data. Pause the video, read through the question carefully, see if you can set it up first, and then unpause the video, make sure you've got it set up correctly, and then pause it again and see if you can solve it. Okay, so pause the video and see if you can set this up correctly. So here, we're given that we're putting a hot piece of metal into water at a lower temperature. So heat is always transferred from the hotter object to the colder object. So the metal will be negative, Q of the metal will be negative because it's going to lose heat. Q of the water will be positive because it's going to gain heat. Now we're given, in our question, we're given information about the specific heat of water, and we're asked for the specific heat of the metal. So we want to re-express or express our Q values in terms of specific heat. So that gives us an equation something like this. Here For the metal, I've got the specific heat of metal, mass of metal times change in temp of metal. Don't forget your negative sign. And for the water, I've got specific heat of water times mass of water times change in temp of water. Now, reading through the question and looking at our data, I plug in the data for the metal and for the water. Again, we're solving for specific heat of the metal, so I know the mass and change in temp. And for the water, I know specific heat, mass, and change in temp. And again, please note that your final temperatures are going to be equal because the metal will lose heat, the water will gain heat until the two come to thermal equilibrium. In other words, until the final temperatures are the same. So pause the video and see if you can solve this. Pay careful attention to your algebra, sig figs, and units. So the first thing I did here was just calculate my change in temp, which is, of course, final minus initial for both the metal and the water. Then I multiplied through these two terms. I multiplied everything over here for the water. Watch your units now. Notice your grams cancel, your degrees Celsius cancel, and you'll end up with joules. Please do not try to solve these problems without including your units. Okay. The next thing, I want to multiply through by that negative sign to get rid of it. And now, once I have this, I want to divide both sides by this number here in order to isolate the specific heat of my metal. So again, keep track of your sig figs as you go. Okay. Once I have that, I can see that to 2 sig figs, the specific heat of the metal should be 0.73 joules divided by grams times degrees Celsius. So again, if you have any questions on that algebra, please go back, rewatch that, but hopefully you got it right.
So let's take a look at another calorimetry problem. Pause the video, read over the question, and see if you can set it up. Okay, so in this question, we're putting a piece of silver into water, and the water is at a higher temperature than the silver. So the water is going to be losing heat, so we have a negative Q for water, and the silver is going to be absorbing heat. So we have the Q value for silver being positive. Now, of course, we need to expand these out. Q is equal to the specific heat times the mass times the change in temp for each of these.
So we've done that here, specific heat for the water, mass, change in temp. Again, then don't forget the negative sign. Specific heat for the silver, mass of silver, change in temp of silver. Now we plug in the data from our question, specifically the water mass. We're going to solve for the final temperature, so final minus initial. Do the same thing for the silver. Remember, include your units. Now the temperature finals are going to be the same because of the thermal equilibrium that's reached. So now pause the video and see if you can solve this. Again, your algebra, pay attention to your algebra, your sig figs, and your units. Okay, so the first thing I did here, I just multiplied these two terms over here, these two terms over here. Again, watch your units. Once I did that, now I went through with distributive property and multiplied the temperature final and the temperature initial by this term right here. Same thing on the other side. Then I multiplied through by my negative sign here on the left side in order to get that out of the way. Now I just moved my terms over to get the temperature finals on the same side and the other terms on the same side. Then I add those two together, and then I add these two terms together. Now I need to multiply through by the inverse of this each side in order to get temperature final by itself. So I multiply both sides by that. These cancel. I'll end up with temperature final by itself. And I get a temperature final of, to 2 sig figs, 82 degrees Celsius. Now again, make sure your temperature, your final answer makes sense. This is higher than the initial temperature of the silver and lower than the initial temperature of the water, so it does make sense. Again, if you did your algebra differently than me, that's fine, but please be sure you can do that correctly. And let's take a look at one last problem. Pause the video, read through this carefully, see if you can set it up and then solve it. All right, so this problem's a little differently. In this problem, you're asked to calculate how much heat was produced by the combustion of TNT. So we're looking for Q of the reaction, or Q of the TNT. Heat is released, so it's going to be negative. Now, in this particular problem, we have two things that are absorbing heat, and that's okay. Q of the calorimetry, so the calorimeter is absorbing heat and the water is absorbing heat. So the Q release, the heat released from the reaction, is going to equal the sum of the heat absorbed by these two objects. Sometimes more than one thing is releasing heat, or more than one thing is absorbing heat. So once we have this equation, now we want to figure out what is the Q of the calorimeter. So we want to re-express solve for the Q of the calorimeter in terms of the heat capacity, not specific heat, but the heat capacity of the calorimeter and its change in temp. So let's do that first. Okay, I've got the heat capacity of my calorimeter, the change in temp. So I can solve that, and I've got the heat absorbed, so it's positive, by the calorimeter. Okay. Now I want to figure out how much heat was absorbed by the water. For the water, we're given the specific heat of water, mass, and change in temp. So we plug in the data from our question. We solve for Q of the water, and we get this number. This amount of heat was absorbed by the water. So now we just have to add these two together. Notice I've kept track of my sig figs as I've gone. So now I need to add these two terms together, and I make it negative because that's the amount of heat that's released. So the Q of the reaction is equal to negative to 2 sig figs, or to the hundreds place, Q of the reaction is equal to negative 12,000 joules, or negative 12 kilojoules. So we could say that Q of the reaction is equal to negative 12 kilojoules, or we could say that the reaction lost 12 kilojoules of heat. Either one of those would be correct. So practice a few more of those. Be sure you're comfortable with the setting them up and performing the math for calculations involving calorimetry.